Hi, this is Michel Bierler. We have seen in the context of simulation how to draw random numbers from random variables. Okay, but now we will see what to do concretely with this. And I would like to give you a specific example of what we call discrete event simulation, which is basically modeling the way a complex system is evolving over time and the occurrence of events that are modifying this system. And I would like to show you the methodology to design and implement this kind of discrete event simulation. There are basically two components that are part of this discrete event simulation. One is a list of variables that we need to keep track of. It's basically about bookkeeping. One important variable is time, because we are keeping track of the time. It's a dynamic system, okay, so we denote it by t. Then we have variables that are counting the events that will occur. We call them counter variables. And finally, there are variables that describe the state of the system at a given point in time. And these are the system state variables. Now, the second ingredients of an event-based simulator are the events themselves. So these events will occur in a given order, so in chronological order. Each of them is associated with a time tag, and we will keep them sorted in chronological order. And the idea is that for each event, we will have to process it. What does it mean? So we take an event in the list, we remove it from the list, and then we update the variables, these variables, and then possibly we generate new events. So the treatment of one event may trigger the occurrence of other events in the future. And finally, we collect statistics because we would like to obtain indicators about the performance of our system. This is why we implement this simulator. Let's take an example. We will consider as a complex system a bar, the bar satellite, which is the bar at EPFL. And the manager of the bar is recruiting a new waiter, and Rico has applied to be a waiter at Satellite. And Rico claims that he's able to serve in average one customer per minute. And the manager would like to understand what it means in terms of performance of the bar itself and level of service. So therefore, the manager would like to use a simulator to answer these two questions. First, in average, how much time will a customer wait until being served? And two, will it be necessary to keep Rico after hours to serve everybody? Let's put things in context. Let's be precise about what we assume about the way the system is working. First, we assume that when a customer is arriving in the bar, she is served immediately by Rico if he is free. Otherwise, the customer must join the queue and wait in line. Then the customers are served using a first-come, first-served logic. Okay, so there is only one queue, and the first customer in the queue is served first. Then when Rico has finished serving a customer, two things can happen, right? So either he's serving the next customer immediately, the next customer in line, or the line is empty, and Rico can just play on his iPhone and wait until the next customer arrives in the bar. Now, Rico claims that he can serve one customer per minute in average, but clearly, depending on the request of the customer, this time will vary randomly. And we will capture this randomness by the random variable xs that will represent the amount of time that Rico needs to serve a customer. And this random variable xs has a PDF, fs. S stands for service. Then we need also to model the time between two customers arriving in the bar. And we will use XA to characterize this time, which is associated with a PDF FA. And finally, we assume that when the closing time, capital T, arrives, a Satellite is not admitting any more customers, but the customers who are still in line will be served. And Rico can leave the bar when everybody has been served. Good, so this is setting up the stage. So now let's see concretely and rigorously how we will implement this and design the simulator. So as I mentioned, the first thing we do is to look at the variables. Here we will have 4 variables. The first variable is time. Okay, t, so this is clear. Then we will have 2 counter variables. NA, which is the number of people arriving in the bar, and ND, the number of people leaving the bar. So it's very simple. And finally, the system variable here is just the number of customers in the system. I denote it by n. Okay, 4 variables. Now in terms of events, well, in our case, there are 3 possible events. One event is the arrival of a customer. The second event is the departure of a customer. And the third event is the bar closes. These are the 3 events that can occur. And I will associate each of these events with a time tag. So TA will be the time of the next arrival of the customer. TD will be the time when the current customer will leave the bar. And actually, if there is no customer currently being served, we will set it to infinity. And finally, the bar will close at a time that will be always the same, it is capital T. So the way we will manage the list of events is that we will always have these 3 events. Then we will update the time tags as the simulation will proceed, and we will keep the 3 events sorted in time so that we process them in chronological order. So let's start initializing the simulator. Well, first we initialize all the variables to 0, right? The time, the 2 counter variable, and the state. I mean, the bar is empty in the morning. Then we have to initialize the events. Well, the first event is the arrival of the first customer in the bar in the morning. Well, to do this, we draw a realization of the variable XA. So we use the PDF FA to draw a realization, and we call it R. So the 3 events are the following. The arrival of the next customer is at time TA equals R. So we have initialized TA. TD is set to plus infinity because there is no customer currently being served. This is the convention we took last slide. And then capital T, this value will not change, is the time at which the bar closes. Good. So we have seen the variables, the events. Now, what are the statistics that we will collect? But basically, we will record each time a customer arrives in the bar, each time a customer departs from the bar, and we will also record the time at which Rico will leave the bar after having served all the customers. Okay, so that's it. That's what we need to initialize the system. Now what we will have to do is that for each event, we have 3 events, we'll have to decide how it will affect the system, meaning that how it will affect the variables and the list of events that we have in our system, in our simulator. So we will take these 3 events one by one. So the first case is that when we treat the event arrival of a customer. So it means that in this case, TA is the smallest of the 3 time tags of the events. So the next event, arrival of a customer. Okay, so we move the time to TA. Okay, so the current time now is TA when the customer shows up. We increase the counter of the number of customers who arrived, NA, and we also increase the number of customers in the system, the state variable. Good, this was easy to update the variables. Now we need to update the list of events. The first event is that when will be the next arrival, but again we draw from the same distribution that we did before, so from the PDF FA, and we update the time of the next arrival. It's T plus R. Now the customer who just entered, we need to update the service time. Well, there are 2 possibilities. Either the customer is joining the queue, and then we don't have to update the service time because it means that Rico is currently serving somebody else. Or it's not the case, and the customer enters the bar and is served immediately. Well, in that case, we need to draw to find the service time. So we draw from the variable XS using the PDF FS, and therefore the customer will be served at time T plus S, which is the new value for TD. Good, so we have updated the events. Remember, we have 3 events, but one of them is always with the tag capital T. This is the bar closing. So we have updated the 2 time tags of the 2 other events. And finally, we collect the statistics, so we just keep record like the fact that at time T, 1 customer has arrived. Good. We go to the next case, which is the departure of a customer. It means that the first event in the list, in the chronological list, is the departure of a customer. So again, we move the time to TD. Then we increase the other counter, the counter of the number of people who departed the system. We update the state by decreasing the number of customers in the system, so we have 1 less customer in the system. And then we need to update the event list. Well, the only events that will be triggered now is the service time, right? So there are 2 things that can happen. So either this guy left the bar and there is nobody else. Well, in this case, Rico can go to his iPhone and play some games, and then we put TD to infinity because Rico is just waiting for the next customer to arrive. If it is not the case, it means that Rico will start immediately serving the next customer. And how much time will it take? Well, again, we draw from the variable XS, and we have a time tag for the next departure. Finally, we keep the statistics. We have a record of the fact that a customer departed at time T. Okay, good. And then we have the final event, which is the closing of the bar. So it means now that when this event happens, that the next arrival of the customer will be after hours, so this guy will not be admitted, and the next customer who will be served is also after hour. So we have 2 possibilities here. Either there are customers still waiting in queue, and then what we do, we have to process the queue. And we basically do what we showed in the previous event. So we move the time to TD, we increase the ND, we decrease N, and we update the service time. We keep the statistic, and we do this as many times as is needed in order to clear the queue. And then at some point there is no more customers. Well, we just need to keep the statistics of the after hour. So, and here in this case, 2 things can happen. Either Rico has been able to serve everybody before the bar closes and then it's 0, or if not, I mean, we have to record the time that Rico spent after hours, which is T minus T. The main message that I would like to convey to you with this very simple example is that doing discrete event simulation is relatively simple. What is important is to be systematic and to have the bookkeeping in a right way. Okay, so you need to be systematic in treating each event in a very specific way. But the good thing is that it decomposes the complexity of the system into these events. Okay, and this is therefore useful to model a very complex system. So let's run our simulator. So I have implemented it as described, and then let's try to see how it works. So here is the scenario that I will be running. So as the service time, as I said, is the time that it is needed by Rico to serve a customer. In average, it is 1, right? That's what we said, 1 minute. And we will assume that it follows an exponential distribution. The second thing is the inter-arrival time. And we will also assume that it's an exponential with mean 1. Actually, if you remember, when we saw the Poisson process, we discovered that in a Poisson process, the inter-arrival time between 2 events is actually captured by the exponential distribution. So somehow here we assume that the customers are arriving using a Poisson process. And for the sake of simplicity, I will assume that it is a homogeneous Poisson process. And again, for the sake of the example, I will assume that the bar is closing after 10 minutes, right? So that's just for the sake of the example. So this is basically an instance of running the simulator. And you have here the list of events, and then each column corresponds to one of the variables that we have been considering. So we have 4 variables that are characterizing the system, so the time, the number of arrival, the number of departure, and the number of customers. And then we have the 3 time tags that are associated with the events. So you see the first event is the arrival of a customer at time 0.94. So we have increased the number of arrival. We have no departure. We have one customer in the bar. And then we have updated the list of events. We have drawn from X A to know what is the arrival of the next customer. We have drawn from XS to know how much time Rico will need to serve this customer. It's not actually good, right? It's 3 minutes 22 seconds. So that's quite a long time. And of course, the last variable is capital T. It will not change during the simulator. The next event is the arrival of a customer. It's at 148, which is the lowest of the three values. And at that time, again, we increase the number of customers, so everything goes in the same way. And therefore, we have actually 4 customers arriving before Rico has finished serving the first client. So we have a line which is forming. So now at this point, we have 3:44 is the arrival of the next customer. 3:22 is the time at which Rico will be done serving the first customer, and this is the closure of the bar. So here, the next event to treat is the next in chronological order. It is the departure event. So we move the time to 3:22. This does not change. We have one more customer departing, so we had none, so now it's 1. Now we had 4 customers, so we have only 3 because 1 left. This does not change. And now we need to serve the next customer in line, and according to the draw, the next customer will be served at 3:49. Okay, so the next event will be an arrival, and so on. Okay, so you see the idea. And then at some point, the next event will be after hours, and this is here, this is happening here. So if you look at the previous event, we had 10:07 for the next arrival, 10:07 for the next departure, at 10 for the closure of the bar. Okay, and at that point there is still one customer in the bar, so the bar will close at 10:07, which is the time at which this customer will be served. Okay, so this shows you the way this simulator is working. So this is one instance of the simulator, and remember, we have collected statistics on the way when we were bookkeeping the variables and the list of events, but we were also collecting statistics. Basically what we did is to keep track of everything that happens for each customer. For each customer we know the arrival time, the departure time, and therefore we can derive the time it took to be served, so the time these people stayed in the bar before being served. Okay, so we have these statistics about the time that customer spends in the bar. And remember, this is how the manager wanted to measure the level of service, by counting how much time people spend in the bar before being served. Okay, so the aggregate indicators that we can calculate to help the manager are: the average time in the system is 175, so this is the mean, the average of the values that I showed in the previous slide, and then Rico leaves the bar at 10:07. But remember, what I showed you was one realization of the simulator, so basically one draw from the random variables. And as I believe now you know, is that you need to do multiple draws, right, before you reach any conclusion. This is what we covered in the first lecture when we talked about the pitfalls of simulation. You never draw conclusions based on only one draw. Now, the good thing with this is that we can basically try other scenarios. So what if Rico works faster, or what if I hire somebody who works faster than Rico? So this is something that is easy to simulate. So here what I've done is to say, well, now let's assume that the service time has a mean 0.2 instead of 1. Okay? And I keep the other two parameters the same. And then I do the same thing. I can simulate all the events, and I will not go through the list. You can just check the instance yourself. But now, as you can see, we have several plus infinity, and remember, this means that Rico is playing on his iPhone waiting for the next customer. And indeed, if you look at the first event, so the first arrival was at 102, and the second one will occur at 314. But Rico needs only 138 to serve the customer, so the customer will leave the bar before the next one arrives. Okay, so this is captured by this scenario, and here we have the case when the bar closes at capital T. Well, basically the bar is empty, so that's it. Rico can leave. His day is done. And we have collected again the statistics for each customer. I have rounded them, so I have here 5 customers. I have the arrival time, the departure time, and the service time, which is the difference of the two. And again, I can calculate the aggregate indicator. Average time in the system is 0.654. Rico will leave the bar at 10 at the closing of the bar, and actually he stops working at 8:51 if you want to know it, which is the departure of the last customer. He's playing on his iPhone the rest of the period. Now that we have seen this example, let's put it in the context of our general framework. If you remember, the general framework was summarized by this equation where we have a system that depends on 3 types of variables, x, y, and u, capitalized because these are random variables. There was some noise, and then we had the indicators capital Z. So in the example of this discrete event simulation, well, the state variables capital X are the time and the number of customers in the system. These 2 variables characterize the system. Then we have an external input that we denoted by capital Y. In this example, this is the arrival of customers. And the control can be here seen as the way Rico is actually influencing the system. He is actually serving customers. So you can see this as the control variable. Now the most important things are the indicator Z. This is actually why we are doing this. And we have 3 types of information that we are collecting. So we are recording the time of each customer in the system. Okay, the arrival time, the departure time, so the duration of the stay in the system. Well, we are also calculating the average time in the system across all customers, and the time at which Rico leaves satellite. Now, something to keep in mind is that the numbers that we have seen that were reported are based on 1 instance. And again, as we have discussed many times, this is definitely insufficient to draw any conclusion based on 1 instance. And remember, the example of Kid City that I presented in the first lecture. So what is important is the distribution of these indicators, the distribution of the time that each customer is spending in the system, the distribution of the average time in the system, and the distribution of the time at which Rico leaves satellite. Now, something important to keep in mind is that when we talk about statistics, when we talk about mean, when we talk about quantiles, whatever, there is a possible confusion in the terminology that we are using. Why? Because the indicator Z itself may be a statistic from the simulator. Right? So for example, what is the mean time spent in the system? Or what is the maximum time spent in the system? Or how many customers are spending more than alpha minutes in the system? So these statistics from the system are generated for each instance. So in a given instance, we have already indicators that are calculated based on a mean, based on maximum, based on variance, based on quantiles, and so on. But still, each of these indicators is a random variable. And we need to generate as many draws as we need in order to collect the distribution of these variables, or of these random variables. And then, once we have the distribution, we can calculate statistics about these indicators. It means that we can calculate things like the 5% quantile of the mean time spent in the system. So the mean time spent in the system means that we calculate for each draw we calculate the mean across all customers. Then we plot the distribution of this mean and we get the 5% quantile. Or we can calculate the mean of the maximum time spent in the system, or the mean of the mean time spent in the system, and so on. So standard deviation of the mean time spent in the system, standard deviation of the number of customers spending more than alpha in the system, and any combination that you deem useful. So what I mean by confusion is that when we talk about mean or variance or whatever, well, we need to be very precise about what we mean, okay? Because you have statistics that are calculated for one instance of the simulator. So basically they calculate mean or anything related to the number of customers, the number of events, or what have you. But then, because each of these indicators is a random variable, we can also talk about the mean, the variance, the standard deviation, the quantile of these indicators. And this is usually bringing a lot of confusion when reporting is done about the statistics. So you need to be very precise about the type of indicators that you are reporting. And actually, before representing this information here, it's always good to first look at the distribution of these indicators and draw histograms. Okay, this is what is recommended. Actually, when you draw histograms, you also have some insight about what are the useful information that you can extract from this histogram. Is it useful to get the mean, or do you prefer to calculate the mode, or maybe you have to look at the statistics in a different way. Let's look at an example. So here I have plotted the distribution of the average time spent in the system by the customers for the scenario where the service time is 0.2 and inter-arrival time is 1 in average. Okay. So if you look at this histogram, so here we have at the x-axis the average service time, and in the y-axis the number of occurrence of each value out of 1000 replication. What we see here is that we have a peak, okay, which is very strange. It seems that there are several values which are 0 actually. So we have to investigate this. So this is why it's useful to plot the histogram, because when I see some things like this, I need to say, okay, why do I have this peak? This is something strange. Because if I don't do this, I will calculate the mean, which is quite low. It's 0.13, and it's due to all these instances where the value is 0. And actually, when I look at this histogram, I'm also interested in the tail. So maybe another statistics that I'm interested in calculating would be the number of days, or the percentage of days where the average time spent in the system is larger than 0.4. And in that case, I have almost 7% of the days are larger than 0.4. Okay, so instead of jumping immediately on calculating the indicators, so here the mean and the quantiles, it's useful to look at the histogram. And here, what I need to investigate now is, why do I have this peak of 0? Actually, what happens is that the arrival time of customer, the mean arrival time, is 0.1. So actually, there are several instances of my simulator where the first customer actually arrives after hours, when the bar is already closed. And actually, I can verify this theoretically. So what is the probability that the first customer arrives before capital T, so before the bar closes? Well, I can calculate it because I know the distribution of the arrival of the customers. And this is 63.2%. It means that almost 40% of the time, the first customer will arrive after the bar closes, and therefore there will be no business that day. And if we go back to the histogram, if you look, this is basically what I observe here. Okay, I have about 400 plus cases where I have 0. Why? Because nobody was actually served by the bar on that day. And the actual number is the following. So in our simulation, there were only 618 days out of 1000 that were actually active, where somebody was served in the bar. Okay, so this is useful because, I have noticed this peculiarity of the results, and I could investigate. So probably here my example is not well defined, so it's not realistic, because capital T is probably too low. I put 10, if you remember, which is not realistic in this case. But still, I can continue the analysis and I can look only at the days where there was actually something happening. So here I have analyzed the statistics where I have removed all what I call empty days, meaning days where there was no customer served in the bar. Okay, and then I can look at this distribution. So basically I have removed the first peak. I have again at the x-axis the average service time, but only during actual working days, and the number of occurrence on the y-axis, now out of 618 realizations. And now I can recalculate the two statistics that I had before. So the mean is 0.20 and the number of days larger than 0.4 is 11%. So actually the number of days is the same, but now it's divided by 618 and not by 1000 as before. With this simple example, I wanted to show the strengths of discrete event simulation. It's extremely powerful. So we decompose a complex system into simple subsystems, and we are basically trying to mimic the real system using this decomposition. And as you can see, things can be decomposed in a way that they are relatively easy to describe, but the most important challenges are in the bookkeeping itself. So we need to identify clearly which variables and which events we are keeping track of. And then we have the statistics. It's really easy to be overwhelmed by the data that are generated by the simulator, right? You can potentially generate a lot of information, and therefore a careful statistical analysis is needed. And I emphasized the importance to distinguish between an indicator, so this capital Z, and the statistics associated with its distribution. So remember, an indicator can be already a mean, or a max, or a variance, or whatever, within the simulator for one draw. Still, it is distributed, and therefore we can calculate statistics of this distribution. There are two things to do to address this last challenge. The first one is to define precisely what we calculate, and the second thing is to start by looking at the distribution, the full distribution, the histogram, in order to get an insight in the indicator and to decide which is the statistic of this distribution that is actually useful.